Here's your Sioux Falls physics teachers moving on to complex circuits. So now we're going to be taking all of these basic ideas on series and parallel and applying them to circuits that combine both together. So we see the circuit diagram given, and it asks for the current through each resistor. Again, a very simple question, but quite a few steps to reach that point. Not difficult steps because they're very repetitive, but we do have to realize that we will be doing quite a few different steps of applying Ohm's law along the way. First thing that we will want to do is calculate the equivalent resistance. And again, when we're going to do that, we want to first label each resistor. So it doesn't particularly matter what order they are labeled in, but for future reference, we'll need to know how we're combining them together. The next rule of thumb, remember, is to start with the smallest possible combination. So here I see that resistance 2 and 3 are connected in parallel. So we want to see what those two would behave like when they are in parallel. For a parallel set of resistances, the value should decrease overall, so we use the inverse equation. This would be 45 ohms and 35 ohms, both to the negative first. And our final answer for the resistance of 2 and 3 together, and notice that it's useful to include that on the subscript for our label, is 19.7 ohms. So now we can think of this combination here as being 19.7 ohms for the two together, and that means that our equivalent circuit is really resistor 1 of 15 ohms in series with the resistors 2 and 3, which are 19.7. So to find our equivalent resistance for the entire circuit, we'll be looking at 15 ohms, and because they are in series, we would simply add them together, added to 19.7 ohms, and that means that our equivalent resistance is 34.7 ohms. Now again, notice that the equivalent resistance was never actually asked for in the question, but before we do any further application of Ohm's law, we need that total amount. Now we can take that amount of resistance and include that in Ohm's law applied to the entire circuit. So we have 6 volts as our total. The equivalent current is our unknown, and 34.7 ohms. Solving for equivalent current, we find that we have 0.17 amps. Now, even though this is not specifically asked for in the question, this is an important amount, because remember that for a series circuit, if we have 0.1 amps leaving the battery, that current then will have to travel first through resistor 1, then continue on to the parallel combination of resistors 2 and 3. So we have, in fact, just answered one of the questions, because all of that 0.17 amps will have to travel through resistor 1. So even though we originally labeled this as equivalent current, we can also label it as current through resistor 1. Now notice that that's not going to be the same as the current going through resistors 2 and 3, because when that charge reaches this combination, it's going to split. Some of it will continue on through the 45 ohm resistor, some of it will continue through the 35 ohm resistor. So we need to be able to figure out which one or how much will go through each resistor. And for that, we're going to need to know the voltage across those two resistors. So again, kind of another step of Ohm's law, not to directly answer the question, but to get us some information that we'll need to answer the question. We know that the total current for 2 and 3 together is 0.17 amps. And we also know that the equivalent resistance for the two together is 19.7 ohms. And so we can find then that the voltage across those two resistors is 3.4 volts. Now that we have the voltage across 2 and 3 together, now we're ready to break it down one step farther and apply Ohm's law to the single resistors. So for resistor 2, the voltage is 3.4 volts. And again, remember, we've labeled this 3.4 as the voltage for 2 and 3 together, but because they are in parallel, they will each get that voltage. The current is our unknown. Resistor 2 was 45 ohms, and that gives us a value for current 2 as 0.076 amps. Now we can repeat the process, which again I've already done here to save us a little bit of time, for resistor 3, again using the same voltage of 3.4, using its individual resistance of 35 ohms, and we get a total current through resistor 3 of 0.097 amps. Now again, notice that between currents 2 and current 3, we have a double check. They should add to give us the same as our total for the circuit of 0.17. And as you get more comfortable, that also will give you a little bit of a shortcut to doing this, because as soon as we found current 2 to be 0.076, we could have just subtracted to see what was left for current 3. So our final answers then, 0.17 amps going through resistor 1, and then splitting for 0.076 through resistor 2, and 0.097 through resistor 3. Hello again from your Sioux Falls physics teachers, looking at another complex circuit. This one with a little bit of a twist. We are to determine the power dissipated in each resistor in the circuit shown below. Now again, notice it never specifically tells us we need to find total amounts for the circuit. And in this case, we're going to be able to avoid a little bit of that by using a few shortcuts. So the first thing that we want to do then is label our resistors, and we have R1 at the top. We'll put R2 at the top also, and R3 as the 110 ohms that's kind of on its separate little path there. The first thing that we want to deal with is R1 and 2. Notice that they are in series, and as such, they are sharing the voltage of the 18 volts that is provided. So if we can find the current through that path, we can easily find then the power that is included. So first of all, for resistors 1 and 2, they are in series. So we would be simply adding the two values together, 84 ohms and 67 ohms. And that gives us a total resistance for 1 and 2 of 151 ohms. Now, really all we need to know is the power that is through there. So the next thing we want to do is apply Ohm's law to these two together and determine the amount of current that is running through that branch of the circuit. So at this point then we are looking for the combination of 1 and 2 together. Notice that together they do get the full 18 volts. And as we have just found, together they have a resistance of 151 ohms. That means that the current between the two of them together is going to be 0.119 amps. Now notice that to find power, our equation is current times volts. So we could go ahead and find individual voltage amounts for these, but also notice that volts could be replaced with I times R from Ohm's law. So if we do a little algebra there, we find that that is really I squared times R. And so rather than finding individual voltage amounts, we can actually take this little shortcut, I squared times R, and apply it to each of those first two resistors individually. So we'll start with resistor 1. We have a current amount of 0.119 amps. That's the amount that's going through this branch of the circuit. And so that means that it is going through both resistor 1 and resistor 2. So 0.119 amps. Resistor 1 has a resistance value of 84 ohms. And that gives us a power amount then of 1.19 watts used in resistor 1. We can then repeat this same shortcut, so I squared times R for the second resistor, which I've done already here to save a little time, using our same current of 0.119 amps and the second resistance of 67 ohms. We get 0.95 for the power used by the second resistor. To find our power for R3 down here, we are going to use another shortcut for our power equation, but this time replacing the other piece of information. So last time we replaced volts right here in the power equation. This time we're going to replace current with V over R. So again, that will give us a shortcut equation of V squared over R. And that can actually very easily be applied to our third resistor. And notice that part of the reason that this is such a useful shortcut for this particular resistor is because it is on its own little path within the circuit. So it does not share volts with any other resistor. So as we plug in our numbers, the voltage then for that resistor is simply the same as the total volts for the circuit, and then we can plug in the resistance value of 110 ohms, and finally that will give us the power for that resistor at 2.95 watts. So in both cases we were able to avoid calculating all the possible values for voltage and current by using our shortcut equations for power in this case. Hello from your Sioux Falls physics teachers. Today looking at how power affects complex circuits. We have three appliances used in parallel at 120 volts. We have a mixer at 225 watts, a microwave at 1,100 watts, and a toaster at 720 watts. We need to determine whether or not they will trip a 15 amp circuit breaker. First of all, notice that our basic equation that compares power to current is simply power equals current times volts. Now we could use this individually on all three of the appliances. So in other words, all of them, because they are in parallel, would have the 120 volts, and so we could get a total current for each one individually. However, it actually is a little bit faster because they are also in parallel. We can use this as the equivalent amounts for the entire circuit. So we have been given 225 watts 1,100 watts and 720 watts, and that gives us a total power, the equivalent power for the entire circuit, of 2,045. If we then plug this value in as the equivalent power, and we already have the voltage as 120 volts, we can then take that to calculate out our total current in this situation. And we would find then, if we multiply out our equation, that we get an equivalent current of 17 amps. So to answer our question then, that 15 amp circuit breaker would be tripped, and we would see those results because our circuit would no longer function. So our answer then is yes, it will break the circuit. Hello everyone, if you clicked on this link, you must want to know a little bit more about how to include a meter in a complex circuit. This particular circuit has 3 lamps together with an ammeter and a voltmeter. The first portion of the question describes how they are connected. R1 and R2 are connected in parallel, and that combination is in series with R3. First, it asks to draw a circuit diagram of this situation, including an ammeter to measure the current through R1 and a voltmeter to measure the potential difference across R3. We're going to begin with a circuit diagram of just the 3 lamps together. So we want R1 and R2 together in parallel. So here's our parallel portion of the circuit. We'll put R1 on the top half at 8.3 ohms, R2 on the bottom part with 12 ohms. This combination is then in series with R3. So that would give us then R3 being attached after that, and we'll put that together with a 6-volt battery, which is shown down here. Finally, then, we want to add our meters. And notice that first of all, it asks for an ammeter to measure the current through R1. Now notice that an ammeter has to be part of the circuit that it is designed to measure. So we actually will need to create a break here and actually insert the ammeter as part of the circuit. Okay, so now it's going to be just measuring the charge. As that charge comes through R1, it will go through that ammeter. The charge that is going through R2 will not be going through that ammeter. So that way we are ensured that we will just be getting the charge that is moving through that lamp of R1. Next, it asks for a voltmeter to measure the potential difference across R3. The nice part about a voltmeter is that it is connected in parallel with the part that it's supposed to measure. So we can put our voltmeter up here and simply draw a line to connect it to the circuit around R3. And again, remember, it is important then that if we look at the leads of this voltmeter, one is connected to the circuit before R3, one is connected to the circuit after R3, and that ensures that it would measure a difference in potential difference as that charge moves through that portion of the circuit. Now, the more difficult part of this question is to determine the reading on each meter. So remembering what our meters are, it was an ammeter through R1. Ammeters are designed to measure current. So basically we are looking for current 1 and a voltmeter across resistor 3. So we are then also looking for voltage across resistor 3. Remember that even though it's not specifically asked for in this situation, it's probably easiest to begin by finding our equivalent resistance for the circuit. So in this case, our smallest combination is going to be the combination of 1 and 2, and they are in parallel. So we can use our parallel resistor equation, which uses the inverses, and find that we would have R1 inverse plus R2 inverse. That's 8.3 ohms and 12 ohms. Again, remember that adding those together will give you the inverse of R1 and 2. So our final step would be to take the inverse of that, and we get 4.9 ohms as the equivalent resistance of resistors 1 and 2 together. Then we can calculate the entire resistance for the circuit, and notice that this would take our combination of 4.9 ohms, that is 1 and 2 together, and add them to the series portion of 5.8 ohms, and we finally get an equivalent resistance value of 10.7 ohms for the entire circuit. Now we can use our equivalent values and apply them to the equation of V equals IR. So again, our equivalent voltage for the battery is 6 volts. Our equivalent resistance was just calculated at 10.7, and that gives us an equivalent current of 0.56 amps. Although this does not directly answer any of the questions, it can help us find first our voltage, and then eventually that will allow us to find our current through the resistor 1 as well. Remember that our equation V equals IR can be applied to any part of the circuit. So in this case, we're going to apply it just to resistor 3. The voltage for resistor 3 is what we're looking for, and notice that resistor 3 is in series with the rest of the circuit. So in other words, if we know how much current is leaving the battery and returning to the battery, all of this current is flowing through resistor 3. So this 0.56 that we've just calculated as the equivalent can also be the current simply through resistor 3. Then we have the resistance value at 5.8, and that allows us to then calculate the voltage across resistor 3 of 3.25 volts. So our voltmeter attached up here should be calculating 3.25 volts as the voltage used across that light bulb. Now our second part of the problem is to determine the reading on the ammeter. And for that we're going to need to know this amount of current flowing just through resistor 1. Well, that will be much simpler if we can find the voltage across resistor 1. And we do know that the total is 6 volts. We also just found that 3.25 volts were used across resistor 3. That then would leave us with 2.75 volts as the voltage across this combination of 1 and 2 together. Now we can go back to our equation V equals IR and apply this just to resistor 1. We have the voltage now of 2.75. Resistor 1 has a value of 8.3 ohms, and so we can then finally solve for that current, and we get I1 at 0.33 amps.